All right, so we're going to get into aircraft systems today, and this lesson is going to be split into two because it's a really huge category. We can't really cover everything in one lesson. If you've already downloaded the slides, I made a couple changes. It's really just cosmetic. None of the material really changed. So today we're going to go off aircraft construction, flight controls, and power plants or engines. So basic components. Talking about the fuselage. So the fuselage is going to be the front part of the aircraft here. Right there. Let me turn on my laser pointer. There we go. So this entire front part of the aircraft, including the cabin and part of the tail cone. Then the empennage is the tail surface towards the back, the purple area here. And then we have our landing gear and power plant. So power plant is going to be the engine and propeller. So getting into the fuselage is front portion of the aircraft. When I went through flight training, I was very confused. Like I always got the two mixed up because on your checklist it says check fuselage, check empennage, and I was like, I don't know which one's which. Fuselage, F, front, made it easy for me to remember, and then empennage is just the other one. So fuselage has gone through a couple changes over the years. So first aircraft kind of looked like this, where it's basically just frames and spars. So this is called open truss. Obviously not the most aerodynamic, saves a lot of weight, but also not the most soundproof either, so it might be hard to hear an instructor. After that was something called a monocoque design, and so there was very minimal structural support inside the aircraft, and the skin of the aircraft actually provided most of the structural support. Easiest way to think about that is like a can. So think about like a soda can or like a tin can. The skin itself was the structure of the aircraft. And so in certain directions, it's pretty strong, but as soon as the exterior becomes damaged or dented, it's weakened a lot, right? So I don't know if you guys ever tried that where you stand on top of a soda can. It's pretty strong, it can support your weight, but as soon as you dent the side of it, it crumples. Currently, in a Cessna at least, we use what's called a semi-monocoque, which is this design here at the bottom. So it uses ribs, spars, and stringers and a couple other things to maintain the structure of the aircraft. And then it's covered with an aluminum skin to make it more aerodynamic. So as we get into flight controls, this is just a very easy way to organize your flight controls. So you have some that are considered primary flight controls and some that are considered secondary flight controls. So your primary flight controls are ailerons, elevator, some cases something called a stabilator, and a rudder. So these are going to be what control the aircraft on the three axes that we talked about before. So roll, pitch, yaw. And then we have secondary flight controls, things like flaps, leading edge devices, trim, and spoilers. So we get into this kind of a mixture of the two. It's kind of hard to organize it between primary and then secondary flight controls, so we'll do kind of a combination of the two. So looking at the wing itself, obviously the primary driver of lift in the aircraft that we talked about last time. So the structure of the wing looks like this. It may be kind of hard to see the labels back there, but you have something called stringers, ribs. They go lengthwise of the wing here, and then a skin that covers the entire wing. And it also houses the fuel tanks. So on the part nearest the aircraft, kind of the root of the wing right here, you have fuel tanks. So you have a fuel tank on each wing. Same with high wing or low wing aircraft. And then we have our ailerons. So we talked a little bit about ailerons last time. So ailerons are on the outer part of the wing here, on the trailing edge, and those control the aircraft's yaw. So whenever you want to turn the plane, you move the yoke left or right, just like you do a steering wheel in the car. Those ailerons will deflect, it'll lift one wing and lower another one, and it'll turn you in the direction that you're wanting to go. It's a pretty simple design. I should be able to zoom in here. So the ailerons are connected to the yoke, and cables are just fed throughout the entire, so the floor and then out to the wing. And that cable is fed through something called a bell crank, which translates that force into a push rod. And so you'll see a push rod that extends from inside the wing to the aileron. And that push rod is what actually moves your aileron. So pretty simple design. Our flight controls most flight controls aren't electronic in a small aircraft. Flaps are the exception. We have an electronic motor on the right wing and a lever right here. So if you look to the image on the back wall here, that's your flap lever. So usually there's some notches or steps to the flaps, and it's divided into degrees. So you have 10 degrees, 20 degrees, 30 degrees, and older models have up to 40. I think Piper has manual flaps, so it kind of looks like an e-brake, if you guys have ever driven manual. So it's in between the two seats and it just looks like a big e-brake. And so whenever you move that lever, it moves your flaps. Downside of that, it's kind of a lot of work to move those flaps, but it is more instantaneous, whereas electronic flaps, you have to wait for the motor to kick in, and it's a very slow deployment of flaps and slow retraction of your flaps. So there's only one motor, it's in the right wing. You don't want isolated flap motors, because if one fails and you have one flap that's being deployed and the other one stays up, it's not very good for stability. And so if your flaps fail, you want both of them to fail together. On that note as well, since they are electric, if you do have an electric failure in the aircraft, you just won't be able to use your flaps. Not necessarily an emergency. You're going to train how to land without flaps. Flaps just help you. It's not a requirement to have to land with flaps every time. So in my experience, most people have better landings without flaps than they do with flaps. So you might notice that as well. So looking at the empennage, or the purple surface here at the back of the wing. So that consists of the stabilizers. So you have a vertical stabilizer right here, a horizontal stabilizer right here, and then the part where that attaches to the tail surface right here is called a dorsal fin. Most people don't talk about it, but you may get asked about it at some point. So the rudder right here is a control surface that's attached to the vertical stabilizer. Then your elevators are attached to the horizontal stabilizer, and then you'll have trim devices that are connected to or attached to your elevator. So the reason why we have horizontal and vertical stabilizers is because they work like the tail of an arrow or dart. So they keep the aircraft weather vaned into the wind. So it just keeps the airplane pointed into the wind. So easiest example of that is, kind of wish I had a dartboard, but if you were to throw a dart sideways, it would eventually turn and point towards the wall or dartboard. It would align itself with the wind, and then it would stick to the dartboard. All right, so looking at our rudder first. So number one right here is your rudder. And that's gonna be attached to the vertical stabilizer, and that controls yaw. So yaw is a left to right motion like this, and that turns the airplane on the vertical axis. So if you imagine just a straight line going through the center of the plane, it rotates the plane on that axis. So it's a secondary flight control because we don't control the airplane with rudder. We don't say, oh, I need to turn right, let me add right rudder and go that way. So it assists your ailerons in performing a controlled and coordinated turn. So generally, if you turn right, like we mentioned last time, you're gonna have adverse yaw, which brings this wing back like that. So now the tail is to the inside of the turn, which is performing a slip. So in order for the tail to align with the nose throughout a turn, is you add right rudder, and it keeps these aligned and coordinated throughout a turn. Easy way to remember it is just use the rudder in the direction of the turn. So if you're doing a right turn, right rudder, left turn, left rudder. And we'll talk about it with our flight instruments on lesson 5. But you also have a turn coordinator, which shows you if you're coordinated, if the nose and tail are aligned. Next is the elevator. So it's on the horizontal stabilizer right here, and that controls pitch. So that's going to be on the lateral axis. If you push the yoke or pull the yoke like that, it's going to move the tail up or down. So it's going to deflect the elevator this way or this way. So if it deflects down like that, it's going to raise the tail, which pushes the nose down. And if you deflect it that way, it's going to push the tail down, which raises the nose. So you notice that just by pulling the yoke up, deflects these like that, pulls the nose up like that. So both of these, just like the ailerons we talked about, are controlled with cables and pulleys. I forgot to mention the rudder is attached to foot pedals. So instead of a gas and brake like you have in the car, you have 2 foot pedals. And those have 2 functions. One of those is to control the rudder. So if you do kind of a sliding motion with your heels, that's going to deflect the rudder like that. And the other function is if you depress the toes, that's going to activate the brakes that are on these back wheels. And we'll talk about those more in a second. And then the yokes are connected to a Y-bar right here, which are connected to more cables and pulleys. And those go all the way back to the elevators. So the elevator, these are connected to a single rod that goes through the center right here. And so these aren't individual, it's just one component. And the elevator trim control system, so we have something called a trim wheel that will be, never mind, it's off the photo. So on the center column right here, kind of towards the bottom, you have a trim wheel. And if you rotate that wheel, it deflects a trim tab that's attached to your elevator right here in the back. And that's basically used for relieving pressures in the aircraft. So if you're flying and trying to maintain an altitude and you feel like you have to fight the airplane a little bit, you can move the trim tab and that'll relieve some of the pressures, because you don't want to go do a 2-hour flight and you're having to white knuckle the whole time and push the airplane down or sometimes pull it up. So it's kind of like cruise control in a sense, is that you should be able to trim the airplane so that way if you let go, it maintains whatever attitude you want it to. So you can trim it for maintaining a climb, you can trim it for maintaining a level flight or even a descent. Most students underutilize trim, and so it's kind of hard to break that habit, especially during stage 1, is they're so focused on maintaining control of the airplane that they over-control it when they can just use trim and make their life a lot easier. I remember probably my first couple lessons in the traffic pattern, I'd go home with like a sore shoulder. Like it would be burning throughout the flight lesson. I was like, man, I really hate traffic pattern. It just sucks. It's because I never touched the trim. So the whole time I was just like white knuckle shaking. It'll make it a lot easier because most of the time you're only flying with one hand. So you want to fly in the left seat with your left hand so it frees your right hand for radios, for throttle, things like that. So this hand is free to do whatever you need it to, and you control the plane just with one hand. So you can turn it, change the pitch. So try and get that habit as well. And if you feel like you have to fight the plane too much, you can just use some trim. It'll make your life a lot easier. Most people want to double hand it, and another habit to break. So we have high lift devices. Our primary one we'll talk about is the flaps. So this is just going into the aerodynamics of how your flaps work. So with your flaps up, this is showing the camber line going from the leading edge to the trailing edge. So if you were to divide the top half and the bottom half of the wing into even halves, it would form the camber line. Now if you were to draw a straight line, there we go, look at this one. So straight line from the leading edge to the trailing edge, that would form your chord line. So just by deflecting flaps, you change the camber and you also increase the angle of attack. So the old angle of attack is this light gray line right here, and then just by deploying flaps, you change the trailing edge you're changing the trailing edge of the plane, and that's increasing your angle of attack. So that's increasing lift. So we'll primarily use flaps for landings in a small aircraft. There are a few specific types of landings where you'll go up to using 10 degrees of flaps for takeoff. Any more than that, these engines really don't have enough horsepower to overcome full flaps. So flaps will increase your lift. They also increase drag. And so that leads to these three advantages right here. So you're able to land at a lower airspeed, which is going to lead to a shorter ground roll, overall safer landing. You could descend at a steeper angle without increasing your airspeed. So if you were to just pitch the airplane down without adding flaps, the airspeed would start to increase and it would make it difficult to land within a safe distance. Also, like I said before, it reduces the length of your landing. So not all runways are, large enough for like a large aircraft to land on, or for us to land if we're going 100 knots or something. So we generally have to slow down quite a bit in order to land within a safe distance. There are a couple different types of flaps or designs. So plane flap. So first image right here is just a basic section of the wing. A plane flap is just a hinged surface on the trailing edge of that flap. So flaps, you'll notice as you begin flying, they change the center of lift, and so you'll notice a few different flight characteristics as you deploy flaps. Next is a split flap. So it's a hinged surface underneath the wing, and so it doesn't change the basic section of the wing, it just drops down underneath the wing. So both of these, I'd say, increase the drag quite a bit without necessarily producing a lot of extra lift. So the other ones that lead to more lift would be these designs right here. So this first one is a slotted flap. And how it's different from our plane flap here is that there's actually a gap or a slot where this blue arrow is going through. So what the slot does is it allows high energy air underneath the wing to go through the slot and then rejoin the air on top of it. So what this does is delays stall. So at some point you would have some air separation on top of the wing, and this slot allows that air to be kind of re-energized and delays the stall. So a slotted flap is going to increase the coefficient of lift a lot more than the previous two that we looked at. Now a Fowler flap also has a slot where this blue arrow is going through, but it also extends rearward. So now you're introducing the slot portion, and you're also increasing the total surface area of the wing. So since you guys have memorized the formula for lift, it's dependent on the area of the wing, so the area and the shape of the wing. So if we increase our wing area, we're also increasing our lift. On airlines, so next time you're sitting next to the wing on a commercial flight, you'll notice that they have slotted Fowler flaps. So you'll see multiple sections to their flaps, and that's to introduce multiple slots. So it has a few different areas where their flaps, or where the airflow can go through the flaps. They also have a higher degree of flaps, so you'll see them almost pointing like straight down for landings. So those are trailing edge flaps. You could also have leading edge devices, so the front of the wing. And really these are just to increase lift as well, just like the trailing edge flaps. So you could have a fixed slot, which is image number 1 right here. And so that would look like this. And so as the airplane gets close to, it pitches up, gets a higher angle of attack, the air is able to go through that slot and follow the upper curve of the wing, also delaying a stall. You could have a movable slat, which would be this one right here. And so that one you would actually have some control over. Leading edge flap. So it would drop down from underneath the wing. Also would have control over that. You could also have a leading edge cuff, which is this design right here. So this is kind of a permanent section built into the wing. So these are going to, especially this one, is going to increase the coefficient of lift and camber, but a downside is your cruising speed is going to decrease because it's going to increase your drag during cruise flight. Most designs, regardless of a training aircraft or an airline or something, are going to have a very similar tail design. Sometimes you have a T-tail where the horizontal stabilizer is on top, like that. You could also have these guys right here with a V-tail. So these have what are called rudder vaders, and so it's an elevator and rudder combined. So depending on the flight controls or your control input, it's able to tell whether you're just trying to use elevator by pitching, if you're also introducing your rudder pedals, and it's going to control the amount of deflection depending on what controls you're putting in. So here's operation of the trim. So there's the trim wheel right there. So it's going to be in the kind of center section of the aircraft between the two seats. So this one actually has elevator trim, which is this vertical wheel, and it has rudder trim, which is the horizontal wheel. Most single engine planes don't have rudder trim. It's usually multi-engine aircraft, but they work the same, just different flight controls. And so you'll see at the top here it says nose down trim, nose up trim, and takeoff position. So there's a white triangle, and you align this white line here with that as kind of a neutral position. So if you feel like you have to push the airplane down in order to maintain flight, like it naturally just wants to climb, you would turn that wheel upward like this. And so you'd rotate it in the direction of this label, and that would deflect your rudder like that. So the trim tab actually deflects upward. So the trim tab deflects upward like that, and as the airflow hits that, it pushes the elevator down, which then raises the tail and pushes the nose down. So it kind of works intuitively to what you think the elevator should be doing. So it deflects opposite, and then the air pushes the elevator the opposite direction. So now if you wanted to do nose up trim, rotate this downward. The trim tab, we'll wait for the next cycle. Trim tab deflects downward like that. The airflow hits it and then pushes the elevator upward. And so as the air hits that elevator pointed like that, it's going to pick the nose up. So there's no set or established settings for trim. It's really just based off of feel. So it really depends on how much airflow is going over the control surfaces. So anytime you change your power setting, you're going to have to change your trim. All right, next we'll get into the power plant. So like I said before, your power plant is referring to the engine as well as the propeller. So the whole purpose of our engine is going to convert chemical energy through combustion into heat energy, and then that gets translated to mechanical energy. So the propeller is eventually going to start rotating, and that's going to produce thrust and allow us to fly. So two main categories of engines we'll talk about: reciprocating engine here at the top, which is what we have, and a turbine engine. So that's about as much as I'm going to explain of the turbine engine. You really don't need to know it for the written test. You don't need to know it as a private pilot. You just need to know what you're actually flying. If you go on to get your commercial certificate, you may be expected to understand a little bit more about the turbine engine, but really anytime you apply for a certificate or you're studying for something, it's really based off of what aircraft you're going to be flying. They're not going to ask you, well, how does a helicopter fly? It doesn't apply to you, it doesn't matter. So since we use a reciprocating engine, that's what we'll talk about. So there's a 4-stroke cycle. The first one is intake. So it's called intake because it allows intake air and fuel to enter the cylinder right here via the intake valve. So this valve opens up, allows your fuel air mixture to enter this chamber while this piston goes downward. Then there's a compression cycle. So this intake valve closes, and so now it's a sealed chamber. And the piston goes up, it compresses that fuel air mixture that was just let in. And then there's a spark plug right here at the top that ignites that fuel air mixture when it's under pressure, and that drives the piston downward, which generates power. So when there's combustion, push that piston down, and then as it rotates, that eventually gets translated to the propeller. Now on the upcycle, so now you have all this burnt gas inside of the cylinder, the exhaust valve opens up, and the piston pushes that exhaust gas out. So in our aircraft, we have 4 cylinders, and so each of these are always on one of these strokes as the engine's going. So you will have to memorize these steps. It's a common question to get asked, at least at our flight school during stage 1, and during a check ride. You'll be asked to explain what kind of engine you have, what are the different strokes, and what's occurring. So once again, intake, stroke, compression, power, exhaust. Easy way to remember it is suck, squeeze, bang, blow. Take that how you will. Wherever your imagination takes you. So the turbine engine works exactly the same in a sense. So there's going to be an intake, compression, combustion, and exhaust cycle. The difference is they're not strokes, it's continuously spinning, and so these are all occurring at the same time, continuously. So generally turbine engines have a better lifespan than reciprocating engines because they're not changing direction constantly and going through different cycles. Turbine engine is just continuously spinning and going through these strokes all at the same time. So you can also supercharge or turbocharge a reciprocating engine in an aircraft. I don't want to disappoint you, but none of our aircraft are supercharged or turbocharged. So the idea behind both is the same, is that as you go up in altitude, air density decreases. And so the intake air that you're using to produce combustion is decreasing. So you're producing less power as you get higher in altitude. And so both of these allow a way to compress that intake air, so you're able to produce more horsepower at higher altitude. A turbocharger is pretty efficient. It just recycles exhaust gas. So if you see this red line here at the bottom, that exhaust gas is bypassed. It rotates a turbine, which rotates a compressor. So the intake air goes through the compressor, and it compresses the intake air that's going to the cylinders. You're able to control how much compression you're producing through a wastegate. So if you're needing maximum compression at higher altitude, you can completely close that. So all the exhaust gas bypasses the wastegate and goes towards this compressor. Whereas at sea level on the ground, you don't need all that compression. It's pretty stressful on the engine. So you would open up that wastegate completely to allow that exhaust gas out. Supercharger has the same idea, except it's using bleed air from the engine to drive a pump, which compresses the air. So some of that power being produced by the engine is going towards powering the pump. So you're sacrificing a little bit of power, but in the end you're producing more power than you would have otherwise. Next is our induction system. So induction system is referring to basically the system or the channels that bring in outside air, mix it with fuel, and then deliver it to the cylinders. So you could have two different types of delivery systems or methods, the carburetor or a fuel injection system. We have a combination, probably like half and half of what we use here. So depending on when the aircraft was produced, you could have a carbureted model for something a little bit older. Most newer aircraft are going to have a fuel injected system. The two main controls for this are your throttle. So like I said before, you don't have a gas pedal in an aircraft. Most people have seen the throttle control on like an airliner and like videos and stuff. So this is ours in a small aircraft. It's just a little push rod. And so this is going to be mounted on the panel right there in the middle. So it's that black knob next to the red one. And so that's why I said you want to fly with your left hand so that way your right hand is available to use that throttle. You can think about it like a gas pedal in the car. So if you push this rod forward, it's like putting your foot down on the gas pedal. So you're giving gas. And if you pull that rod out, it's like taking your foot off the gas. So the throttle is controlling how much fuel or mixture you're letting into the cylinder. And you have this red lever next to it. That's called mixture. And so that's controlling how much fuel you're letting into the mixture of the fuel and air. So the reason why we need to control it is because as you go up in altitude, like I said before with the turbocharger, air density decreases. And so you need less fuel as you get higher in altitude. If you were to leave it all the way forward, it's letting in a maximum amount of fuel. And so I'll show you right here. So ideally, fuel is like, the ratio is about 14.7 to 1. So 14.7 parts of air to 1 part of fuel. So I usually just round it, so 15 to 1. So usually everything in chemistry requires a ratio in order to produce the most heat or energy, and that's what it is for fuel. Just to make the explanation a little more simple, we're just going to say it's a 1-to-1 ratio. So looking at the bars here at the bottom, if the light blue is your air and the purple one is your fuel, if we're at sea level and everything is perfectly balanced, we have a 1-to-1 ratio. Now, if we climb to 10,000 feet without adjusting the mixture, the air density decreases, so this side will begin to drop. And if we left the mixture all the way in, it's considered rich. And so that ratio would be off. We'd have too much fuel for the amount of air that's available. So this is called a rich state. So what we do as we climb is we pull that rod out. It's usually threaded, so you can spin it and it'll come out. Or you can push this silver button and do larger changes, and it'll slide out, you can slide it back in. So as you go up in altitude, you lean the mixture, or you pull that mixture out, and it allows less fuel into the fuel-air mixture because air is less dense.
Is it dangerous to run a rich engine?
Yeah, so reason why it would be dangerous is because if you have too much fuel that's going into the system, you can't burn all of it, and so you get built up on the spark plugs. And eventually, if there's enough built up on the spark plugs, they can't fire, and so they would just fail. Yeah, so if you have one cylinder that's not producing any spark or combustion, suddenly you get down to 3 cylinders, you have a lot less horsepower, and it's pretty common that if one spark plug has failed or one cylinder has failed, the rest are going to follow suit because the same condition has occurred in all of them. There are some conditions where you would want to be a little more rich. It does have a cooling effect. So if the engine's running kind of hot, you would richen the mixture a little bit, and some of that vaporized fuel would help cool the engine. So yeah, let's say go back to 10,000 feet right here. We've leaned the mixture, so everything's perfectly balanced again. And then without adjusting the mixture, we go back down to sea level to land. And so now the air density has gone back up at sea level, but we've left the mixture out. So now it's a really lean mixture. And so there's not enough fuel to match how much air is going in. So in that case, you could get engine roughness. If it's lean enough, the engine could just shut off because you're kind of starving it of fuel. So usually when we shut the engine off, we don't just turn the key off like a car. We usually pull the mixture all the way out. So it burns up any fuel in the system, and then we take the key out. And so if you're excessively lean, you could have roughness, or the engine could just stop. So anytime we're changing altitude, climbing or descending, we're always adjusting the mixture.
So is the equivalent to like a car, would that be like flooding it?
Yeah, flooding would be too rich.
Okay.
Uh-huh.
Right. So and it causes it to stall.
What was that?
I was going to say that.
Okay.
Probably stall it.
Yeah.
Could you fire back up though in the air? Like if it was too lean and the engine shut off on you?
Oh, yeah.
Fire it back up?
Yeah.
Okay.
Yeah, so usually the prop, if you shut it off, it will continue windmilling, meaning the prop is still spinning because of the airflow. And if you put the mixture back in, it should just start back up. So I've had students accidentally shut off the engine before, and you just push it back in. If it doesn't come back on, just get ready to land. Usually doesn't require that, but cool. Any questions about this?
I'm sorry. So
No, you're good.
That mixture level stick,
Mhm.
does that like, I don't know, a better way to say it, like clicks to it, like as you're pulling out, click, 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 that could
No, so
one smooth, like trend all the way.
if you push the button, it's smooth. You can do major changes or like really small ones, or if you spin it, you can get pretty small increments because it's threaded.
So it's all based on touch and like feel of the plane.
Yeah, so if you're just climbing up slowly and you need to make really minor changes, you can just bring it out slowly, do a couple twists, leave it, do a couple twists, leave it.
So it's kind of like a clutch, right? Like I imagine like an experienced pilot like you probably can read your engine or listen to it sound differently. Is it based on sound and feel? Is it?
A little bit of both, depending on, so more advanced systems like the one with the screens in the back there actually have a system that can help you. It's called Lean Assist. And so it brings up all of the cylinder temperatures, and it'll identify which one's the hottest, and then you keep leaning it and it reaches a peak in temperature, and you operate a little bit cooler than that peak. And so the system will tell you, which is kind of cool. Otherwise, there's some gauges that'll tell you exhaust gas temperatures or cylinder head temperatures. You could do it that way. Old school method is just lean it until the RPMs peak, and then once they start to drop off, or if the engine starts to get rough, then you just put it back in a little bit. So that's kind of like the rule of thumb method. So usually we lean the mixture on the ground. So as soon as you start the engine up, we don't have this all the way rich. We'll usually lean it out a little bit. Just because with the RPM so low, we don't need very much fuel. Otherwise, we would foul some spark plugs on the ground. So on the ground, easy way to do it is just lean it until the RPMs start to peak. And if they start to drop off, or if the engine gets a little rough, just do a couple twists back in. And then if you add some throttle to start rolling and you notice the engine's really rough, just enrichen it a little bit and you're good to go. I'd say most flight schools, especially here, a really common problem is people don't lean enough on the ground. And so spark plugs get fouled. And so they just have to replace them. So here's an induction system. So here's the spinner, which is kind of this cone on the front of the plane right here. So underneath that, you have an air filter just below the prop, and that's where the air is getting drawn in from the environment. So you have an air filter right here. This is a carbureted model, so most people imagine a carburetor on top of the engine. In an aircraft, it's actually below, and it draws it up. So the intake air goes through here, then it gets drawn up through a carburetor or a fuel servo, depending if you have a fuel injected model. So here is a simplified version of a carburetor. So we use a float type carburetor. So that means is there's a small chamber or reservoir that stores a little amount of fuel, so that way you have a continuous flow through the carburetor. If this was drawing directly from the fuel tanks, there might be some delay or it might not flow quite as smoothly. You can also think about this like the tank on the back of your toilet. So whenever you flush, water comes from the tank, goes to the toilet, there's a ball inside there that drops, it opens a valve, lets more water fill up the tank. Same thing is happening inside this carburetor. This float drops. There's a fuel inlet, it lets more fuel inside this chamber. That pushes the ball up, or the float, and then that shuts off the fuel inlet. Usually, as you're flying, you're burning up fuel, and so this float will drop a little bit, so you're continuously letting fuel in and burning fuel. So from there, you have a discharge nozzle right here, which is allowing vaporized fuel inside the throttle valve right here. So what happens is whenever you add throttle, you open the throttle valve. That allows more air to be drawn in through this air inlet. And going back to aerodynamics, as air passes through this venturi, which is kind of this narrow section right here, the air velocity increases, which decreases the air pressure at this location. So right here, you have really low air pressure because it's going faster. So that change in pressure, now you have higher pressure inside the chamber, lower pressure here. Pressure wants to go from high to low, so it's going to push fuel from here and vaporize it in this throat right here. It's very, I would say, reliable design. Carburetor's been around forever, been on motorcycles, cars, airplanes. Major disadvantage would be carburetor icing. So because you experience an increase in velocity and a pressure decrease right here, that also leads to a drop in temperature. So you can get a buildup of ice in the venturi right here, on the throttle valve right here. So this would essentially restrict how much fuel air mixture you're letting through. And so that would, again, starve the engine of fuel air mixture. So with carburetor ice, you would probably notice a decrease in RPM or engine roughness. And carbureted models have something called carb heat, which is a small lever that you pull, and it allows hot air, usually coming from around the exhaust, to go through here, get mixed with the intake air, and so now you're melting the ice. So it's mixing with the intake air. It's not completely like hot air to the point where the hot air is going to decrease your performance as well. It's just warmer. So that warm air will melt the ice. And a common written test question is, you experience a drop in RPM or engine roughness, you suspect carburetor icing, you apply carb heat, and then kind of what should you expect at that point? Usually you'd have a further decrease in RPM because now you have a restricted carburetor and you're also introducing warmer air. So warm air is less dense than cold air. So now you have a restriction and you also have warm, less dense air. So that's going to drop the RPM initially, and then once the ice melts, that restriction goes away and the warm air isn't going to affect it quite as much as the restriction. So usually we'll use carb heat anytime you're in these conditions, so below 70 degrees and high humidity. Usually for anytime you have a low RPM setting is a good chance you could get carburetor icing. So descents or landings in a carbureted model, you would apply carb heat. So fuel injection system, same concept, a couple different components. So it goes from the fuel tank, the option of going through an auxiliary fuel pump. There's an engine-driven fuel pump. Then it goes through a fuel air control unit. On top of the engine, there's a distribution valve or manifold valve that distributes fuel to each of the cylinders. And sometimes in the cylinder or just before the cylinder, it gets mixed with the air. Overall, fuel injection is more efficient. it's more responsive. So a fuel injected model will have more throttle response than a carbureted model. A disadvantage is it's going to be a little bit harder to start when it's warm out. Anybody that rides motorcycles may know that it's kind of hard to start a bike when it's already hot, especially if it's a fuel injected model. There's a few steps to make it a little bit easier, but for the most part, it might be a little bit harder. I'll take that over carb ice any day. It's going to be a little more sensitive to contaminants and something called vapor lock. So if you're taxiing on the ground in Phoenix in the middle of summer, some of that fuel could get vaporized in the fuel lines, or it could form bubbles. And so there's not a continuous flow to the engine, so your engine could stall. There's a few designs in the system to help reduce that, but I'll get to that later. All right, landing gear. It's right here. It doesn't go anywhere. It's a pretty simple system. You don't need to memorize anything really. So our landing gear includes the main wheels, which are the two back wheels. So these are main wheels right here, and a nose wheel. So the main wheels have brakes, which I should have an image coming up soon. I'll show you. And then the nose wheel does not have any brakes, but it does have a strut. And so it has a little bit of suspension to it. So it's, again, going back to motorcycles, it's kind of like a fork on a motorcycle. So it's filled with air and oil, and it absorbs some of the impact on landing. Not a lot, so don't try and beat up the aircraft. It's not designed for it. So our brakes are hydraulically actuated. So the rudder pedals, like I said, also serve as brakes. So if you depress the toes on the pedals, it's going to provide pressure to the hydraulic line, and it's going to clamp the brake pads on the disc that's on the main gears. So you can actually see them pretty easily. So when you're doing a pre-flight, you can inspect the brake pads, the brake lines, make sure there's no leaks. Getting into propellers. So the prop is what generates our thrust. Like we talked about with the power plant, converts chemical energy into mechanical energy. And so propeller blades are actually twisted. Might be a little dark to see this image. Let me turn this back on. So in this image right here, you can see the propeller blade is twisted. So at the root of the prop, it has what's called a higher pitch, kind of a steeper angle to it. And as it gets closer to the tips, it has a lower pitch, so it's a little more flat. So the reason for that is, if you look at the image at the top, as a propeller blade spins this direction, the wing tips actually rotate at a faster velocity to get to the same point. So this is just an example. This isn't, you don't need to memorize this or anything, but so the tips of the propeller blade are going 389 knots, whereas the root is going 100, it's kind of blocked off, 129. The takeaway is the root of the prop is going slower than the tips. So in order to have an even distribution of thrust across the blade, you need to twist it. If it was perfectly flat, you'd have a lot of thrust being produced at the wingtips and very little at the root, just because the tips are going faster. And so in order to have an even distribution of thrust, they twist it. So that way there's a higher angle of attack where it's slower and a lower angle of attack where it's faster. Again, it's just balancing the lift equation. And so higher angle of attack, you can use a lower airspeed. And then higher airspeed, you can use a lower angle of attack. The two categories of propellers we'll talk about are fixed pitch and constant speed. So a fixed pitch is basically what we use in all small training aircraft. So the blade is just one piece. So no matter which side you're looking at, it's just one connected piece. And it's attached in the center right here. And so if you were to look at the propeller blade, there's a hole in the middle where it mounts, and then it gets bolted onto the aircraft. And each side of the blade is just one large piece. So it's called fixed pitch because the pitch of the blade does not change at all. So once it's mounted, that's the performance that you get. You can have propeller blades that are designed to climb really well, that have really great cruise performance. Most try to be a jack of all trades, where it's okay at climbing, it's okay at cruise, but it's not really great at anything. It's not efficient at one particular thing. A constant speed propeller has the advantage of that you're actually able to control the blade angle. And so each blade is attached individually to the hub, and you're able to control the blade angle. So if you look right here, just by controlling the prop lever, you're changing how much oil you're allowing into this chamber right here, and that controls the blade angle. So the reason why you'd want to do this is just like gears on a bicycle. You're able to climb a hill, or you're able to maintain speed on level ground or while you're going downhill. So with a constant speed propeller, you're able to get the most performance out of every situation. So for takeoff and climb, you can have a lower blade angle, and for cruise, you can have a higher blade angle, so it's taking larger scoops. So when I say larger scoops, it's almost like having the lowest gear on a bicycle and then going uphill and you're pedaling really fast. And then when you get to level, it's almost like a beach cruiser where it's like really heavy, hard strokes. So that's kind of what a constant speed propeller blade is doing, is as it gets to cruise, it's at a higher pitch angle, and so it's taking larger scoops, but you're operating at a lower RPM. So it's going to be more efficient at those phases. Just like everything else, you're not going to be flying constant speed propeller at this point, so don't stress too much about it. When you get onto multi-engine training, however, you will be expected to understand everything happening in all this. So another look at a propeller blade. So we looked at this with aerodynamics, but the prop is basically a rotating wing. So it has its own chord line. It creates its own angle of attack with the relative wind as it rotates. So as it does that, it's creating lift just like your wing would. It's creating an area of low pressure, an area of high pressure, as well as a downwash angle that's going rearward, which we know is thrust. So if you stand in front of a fan, you feel it blowing on you. That's basically what a propeller is doing. It's blowing air backwards, also creating area of low and high pressure. And a couple terms, you have something called brake horsepower. So that's the amount of power produced at the crankshaft. And then thrust horsepower is the amount of power produced by the propeller. The reason why there's different terms is because there's always going to be a loss of power at some point. So for every step, there's some loss in efficiency. So engines aren't very efficient to begin with. A lot of the heat produced by combustion is lost from the engine. That doesn't translate to 100% efficiency. And then the difference in brake and thrust horsepower is going to be between 50 and 87%, like it says right here. There's something called geometric pitch. So that's the distance the propeller should travel based off of its design. So if you think about it like a nut and bolt, so based off the measurement of the threading on that bolt, how far should the nut travel when you spin it? That's kind of what you're doing with the propeller blade. So based off of the designed angles, if I rotate it, how far should the plane travel? Effective pitch is how much it actually travels through the air once it's spinning. Again, because there's some loss in efficiency, you have propeller slip, which is the difference between geometric and effective pitch. Again, you're not going to be asked about this on a checkride or a written test. It's kind of just understanding a little more details. So we'll finish up with this one. Generally in stage 1, you will be expected to memorize these details of what kind of engine you have in your aircraft. So Lycoming is the brand of our aircraft. It's not a Cessna engine. It's made by Lycoming. And this specific model is this code right here, IO360L2A. We have horizontally opposed cylinders. So most people imagine cylinders as going vertically, or the piston moving vertically like this. It's horizontally opposed, meaning the cylinders are on their sides and they're opposing each other. So when they move like that. Our engine is air-cooled, so we don't have any specific cooling system in our engine. It's not liquid-cooled. We just use the airflow over the engine to cool it. It's naturally aspirated because it's not turbocharged or supercharged. We're just using ambient air pressure as our intake air. And direct drive, so the propeller is mounted directly onto the engine. There's no system of gears or belts between the engine and the prop. So that is L-hand. So generally during your stage 1 check, you'll get asked about this, and so it's a good idea to memorize it. Next time we'll go over, I would say this is more of an introduction. Next time we're getting into more details like the fuel system, the electric system, the oil system. I think anything else. Mostly those. And then lesson 5 after that will be aircraft instruments. So the instruments you see on the panel right there, we'll talk about those on lesson 5. Lesson 6 is going to be the stage 1 exam. So it's going to cover everything what we've talked about lessons 1 through 5. Easiest way to prepare for that is review the reading, which everybody loves. Review the question, so go through the sporties based off the topics we've talked about so far, and then go through the practice questions, make sure you understand them. And the questions that come up on the stage test are going to be very similar to that. And so if you feel comfortable with the categories on sporties, then you'll do well on the stage test.